Hello everyone, this is Qingxia. I'm a PhD student from Nanjing University. I'm going to present our work, ESBM, an entity summarization benchmark. This is a joint work with Gong, Cheng, Kalpa, Gunaratna, and Yuzhong. Here's the outline of this presentation. So first, what is entity summarization? An entity in RDF data can be described by a large number of tuples. Entity summarization is the problem to automatically generate a concise summary for an entity. Formally, an RDF data T is a set of RDF tuples describing information of real-world entities, where each tuple has three parts: subject, predicate, and object. For a given entity E, the entity description for E consists of the set of RDF tuples which describe this entity. That is, this entity appears as the subject or object of the tuple. Since all these tuples have this entity as a common part, we can present each of these tuples as a property value pair of entity E. And there are three kinds of values: class, entity, and literal. A class like scientist, person, an entity like Royal Society, England, and literal such as a number, a date, or a string. Given an entity E and a size constraint K, the task of entity summarization is to select a subset of tuples from the entity description of E and satisfy the size constraint of containing at most K tuples. This summary is presented to end users to satisfy users' information needs. Entity summarization supports a multiplicity of applications, like entity cards displayed in search engines. Entity summarization has led to fruitful research, and what we concern is about the evaluation of entity summarizers. This table lists the existing benchmarks for evaluating entity summarization. Some of them are task-specific, like Who Knows Movies for the domain of movies. And all of them each contains entities from a single dataset. It is not surprising that these benchmarks are not very large, since it is expensive to manually create high-quality summaries for a large set of entities. And unfortunately, some of these benchmarks are not publicly available at this moment. The two benchmarks created for evaluating faces and faces E, classes or literals are not included because they could not be processed by their proposed entity summarizer. So obviously, there are four limitations from existing benchmarks: task specificness, single dataset, small size, and triple incomprehensiveness. So there are two challenges for entity summarization research: a lack of good benchmarks and a lack of evaluation efforts that cover the broad spectrum of existing systems to compare their performance. It motivated our work to address these challenges. In this work, we created an entity summarization benchmark, ESBM, to overcome the limitations of existing benchmarks. And to be a successful benchmark, it is designed to meet some desideratum. And with this benchmark, we evaluated entity summarizers, including 9 existing general-purpose entity summarizers and a supervised learning-based entity summarizer. And this is the most extensive evaluation effort to date. So next, I'll show how we created the ESBM benchmark. The creation of ESBM has two main design goals. First, to be a successful benchmark, we designed ESBM to satisfy 7 desiderata for benchmarking. Then, according to the motivation of this work, our design of ESBM aims to overcome the limitations of existing benchmarks. First, the ground truth summaries in the benchmark are general purpose and summaries. Second, to overcome the limitation of triple incomprehensiveness, the benchmark includes class-valued, entity-valued, and literal-valued triples. Third, it contains entities from multiple datasets. It is currently the largest available benchmark for entity summarization. To form the entity descriptions, we sample entities from 2 datasets of different kinds: an encyclopedic dataset, DBpedia, and a domain-specific dataset, LinkedIn. Entities are sampled from 7 large classes. For DBpedia, we sample entities from agent, event, location, species, and work. They collectively contain 60% of the entities in the dataset. While for LinkedIn, we sample from film and person. We extract their entity descriptions from the RDF datasets, and finally, the number of triples in an entity description in each class is in the range of 25.88 to 52.44. And the overall mean value is 37.62. We invite 30 researchers and students as users to create ground truth summaries for the entity descriptions of 175 entities which we sampled for the benchmark. Each user is assigned 35 entities, and each entity is assigned to 6 users. We let each user create 2 summaries for each entity, one containing 5 triples called top 5 summary, and the other containing 10 triples called top 10 summary. We implemented a web application to help users to read and select triples, and this figure shows a screenshot of the interface. Finally, we get 6 top 5 summaries and 6 top 10 summaries for each entity, and the total number of ground truth summaries is 2,100. The benchmark we reported in this work is ESBM version 1.2, the latest version of ESBM, and it specified Cheng validation test splits for 5-fold cross-validation. The early versions of ESBM have successfully supported the anti-summarization shared task at the EYRE 2018 workshop and the EYRE 2019 workshop. Obviously, ESBM overcomes the limitations of available benchmarks where we previously discussed. It also meets the 7 desiderata we considered as design goals. For accessibility, ESBM is publicly available and has a permanent identifier on w3id.org. For affordability, ESBM is with an open source program and example code for evaluation. The cost of using ESBM is minimized. For clarity, ESBM is documented clearly and concisely. For relevance, ESBM samples entities from 2 real datasets that have been widely used. The anti-summarization tasks are natural and representative. For solvability, An anti-description in ESBM has at least 20 triples and a mean number of 37.62 triples, from which 5 or 10 triples are to be selected. The summarization tasks are not trivial and not too difficult. For portability, ESBM can be used to evaluate any general-purpose anti-summarizers that can process RDF data. For scalability, ESBM samples 175 entities from 7 classes. It is reasonably large and diverse to evaluate mature anti-summarizers, but is not too large to evaluate research prototypes. In the next section, we will present detailed analysis about the ESBM benchmark. First, here are the basic statistics about ESBM. It contains 175 entities, and there are collectively 6,584 triples in the anti-descriptions, and 2,100 ground truth summaries are created. Among all the triples in the anti-descriptions, 37.44% of them are selected into at least one top 5 summary. However, many of them are selected only by a single user. 20.46% are selected by different users into top 5 summaries. We may also be curious about the overlap between the top 5 and the top 10 summaries created by the same user for the same entity. The mean overlap is 4.91, which is quite close to the size of top 5 summary, showing that the top 5 summary is usually a subset of the top 10 summary. These two figures show the triple composition of anti-descriptions, the top 5 and the top 10 ground truth summaries. The figure on the left presents the average number of triples of an entity in these 3 sets of triples. It shows that class-valued and entity-valued triples occupy a considerable proportion of anti-descriptions in DBpedia, and entity-valued triples predominate in LinkedIn-DB. Literal-valued triples account for a small proportion in both datasets. However, they constitute 30% in top 5 ground truth summaries and 25% in top 10 summaries. Anti-summarizers that cannot process literals will ignore these notable proportions, thereby significantly influencing their performance. The figure on the right presents the statistics in terms of distinct properties. We found that the average number of distinct properties in top 5 ground truth summaries is 4.7, which is very close to the size of top 5 summary, indicating that the participants are not inclined to select multiple values of a property. Existing anti-summarizers that prefer diverse properties may exhibit good performance. Then we analyze entity heterogeneity in ESBM. Entities from different classes are described by different sets of properties. For each class, we identify the set of properties describing at least one entity from the class, and the Jaccard similarity between property sets for each pair of classes is presented in this figure. You can see all these values are very low, showing the heterogeneity of anti-descriptions. And such heterogeneous anti-descriptions help to assess the generalizability of an anti-summarizer. For ground truth summaries, we list the popular properties that appear in at least 50% of the ground truth summaries for each class. In this table, you can see universal properties like IDF type and also class-specific properties like birth date for agent, family for species, and so on. We found that among 13.24 distinct properties describing an entity, only 1 to 2 of them are popular in top 5 ground truth summaries. It means the importance of properties is generally contextualized by concrete entities. Therefore, it would be unrealistic to generate good summaries by manually selecting properties for each class. Then, we analyze the iterator agreement of the ground truth summaries. We calculate the average overlap between the 6 ground truth summaries created by different users for each entity. The results of ESBM shows a moderate degree of agreement and is generally comparable with those reported for other benchmarks in the literature. Then we can use the ESBM benchmark to evaluate anti-summarizers. In this evaluation, we consider 3 kinds of anti-summarizers. The main part consists of 9 existing general-purpose anti-summarizers. We re-implemented 6 of them, while Maxim, Fabric, and Kalpa are open source. The second part is an Oracle anti-summarizer, which we implement to approximate the best possible performance on ESBM and form a reference point used for comparisons. Oracle simply outputs k-tuples that are selected by the most users into ground truth summaries. The third is a supervised learning-based anti-summarizer. Existing general-purpose anti-summarizers are unsupervised. We implement this supervised learning-based anti-summarizer to explore the potential of this kind of technique. We implement 6-point-wise learning to rank models provided by Weka and use 7 features to describe each tuple. 4 of these features are used by existing anti-summarizers, and we also add 3 binary features. I'll introduce the details later. To evaluate a machine-generated anti-summary SM with a human-made ground truth summary as edge, we use precision, recall, and F1 as evaluation criteria. We will trivially have P equals to R equals to 5 if SM and the SH contain the same number of triples. However, some summarizers, like Diversum, may output less than k triples. In this case, P does not equal to R, and we should rely on F1. Here's the F1 results of existing anti-summarizers and the Oracle on the 2 datasets of ESBM under 2 size constraints. We can see the best results are generated by Fabric, Maxim, and CD under different settings. Fabric achieves the highest F1 under k equals to 5. It significantly outperforms 6 existing anti-summarizers on DBpedia and outperforms all the 8 ones on LinkedIn. It is also among the best under k equals to 10. The F1 scores of Oracle are in range of 0.595 to 0.713. The gap between the results of Oracle and the best results of existing summarizers is still large, suggesting that there is much room for improvement. Then we break down the results of existing anti-summarizers into 7 anti-types. When k equals to 5, There is no single winner on every class, but BAFRIC and MapZoom are among top 3 on 6 classes, showing relatively good generalizability over different entity types. When k equals to 10, MapZoom is still among the top 3 on 6 classes. Kafka is among top 3 on 5 classes, also shows relatively good generalizability. We then analyze the results of the supervised learning-based methods. We can see that among the 6 methods, random forest achieves the highest F1 on DBpedia, and RapTree achieves the highest F1 on LinkedIn. Comparing with the previous results, multi-layer perception, additive regression, RapTree, and random forest outperform all the existing anti-summarizers on all the settings. The rest 2 methods, SMO-RAG and linear regression, only fail to outperform in one setting. These results demonstrate the powerfulness of supervised learning for anti-summarization. Furthermore, we are interested in how much the 7 features contribute to the good performance of supervised learning. For a triple T in the anti-description with property P and value V, the 7 features are G of GFT means global frequency of property. It's the number of triples in the dataset where the property P appears. LF means local frequency of property. It's the number of triples in the anti-description where P appears. VFT, short for value frequency, it's the number of triples in dataset where V appears. SI means the self-information of triple T, and the 3 binary features indicating whether V is a class, whether V is an entity, and whether V is a literal. This table shows the results of random forest after removing each individual feature. Considering statistical significance at the 0.05 level, we can see that GFT and LF show effectiveness on all the settings, and VFT and SI are only effective on LinkedIn. However, the usefulness of the 3 binary features is not statistically significant. So, in summary, this evaluation shows the following findings. Among the existing anti-summarizers, BAFRIC and MapZoom shows the highest performances. However, none of them are comparable with our straightforward implementation of supervised learning methods. And all these results are still far away from the best possible performance represented by Oracle. Therefore, anti-summarization on ESBM is a non-trivial task, and we invite researchers to experiment with their new ideas on ESBM. And this is the final part of this report. First, I'll discuss the limitations of this work. The evaluation criteria we used in the experiment is F1 score, which is based on common triples, but this will ignore semantic overlap between triples. However, it is difficult to quantify the extent of overlap, particularly when multiple triples semantically overlap with each other. In future work, we will explore more proper evaluation criteria. Then, about the representativeness of ground truths. In ESBM, the ground truth summaries are created for general purpose, and accordingly, we use them to evaluate general purpose anti-summarizers. However, for specific tasks, these summaries may not show optimality and the participating systems may not represent the state of the art. Still, it is valuable to evaluate general-purpose systems not only because of their wide range of applications, but also because their original technical features have been reused by task-specific systems. In the future, we will extend ESBM to a large scale and will consider benchmarking the task-specific entity summarization. Third, about the form of ground truths. In ESBM, we provide ground truth summaries. However, there are some other benchmarks provide ground truth scores of triples. Both methods have their advantages and disadvantages. In future work, we will conduct scoring-based evaluation to compare with the current results. Finally, here are some take-home messages of this work. In summary, we have two main contributions. We created an anti-summarization benchmark, ESBM, overcoming the limitations of existing benchmarks. Then, we evaluated general-purpose anti-summarizers with ESBM, which is the most extensive evaluation effort to date. The ESBM benchmark is currently the largest available benchmark for anti-summarization, and the evaluations show that anti-summarization on ESBM is a non-trivial task. If you want to learn more about ESBM or if you want to use it, you can visit this permanent link, or you can visit its repository on GitHub. At the end, I'd like to say a few words about our upcoming paper, Neural Entity Summarization with Joint Encoding and Weak Supervision, which has been accepted by the EJK conference of this year. We proposed a deep learning-based anti-summarizer, and it significantly outperformed all the existing systems on ESBM. That's all. Thank you for listening.